This is Linux In-Laws, a podcast on free Libre open source software, broadcasting from the United Kingdom and Germany.
Welcome to Linux In-Laws, Season 2, Episode 59. Martin, how are things on this beautiful summer day? I think. Maybe not.
Have you been outside?
Not recently, no.
Not recently? No, you're still stuck in the hospital or not? I don't know. Who knows? Anyway.
Doesn't matter, Martin. Doesn't matter.
Yes.
Just keep on. No, I mean, I just came back from this very, very, very short break that Vanessa invited me to. Yes.
Oh, exciting.
If you remember the Christmas episode, there was some talk about a short break. Oh, sorry. So that was cut out, actually, because of the post-production department you just fired.
Ah, good.
Alongside,
we don't want any nonsense in our episodes.
By the way, we did receive 2 applications from a certain David and a certain Thomas.
Oh,
about marketing. Yes.
Oh, about marketing. Ah,
yes,
well, maybe they should focus on making some episodes instead.
Okay, fair enough. This is not an episode about sparse episodes, but rather an episode about Coreboot. So with that, I would like to introduce Julius Werner, but before I even get things more wrong, Julius, why don't you introduce yourself?
Hi. So my name is Julius. I'm working for Google, and I've been working on firmware for Chromebooks for the last 13 years. And as part of that, we do use Coreboot on these devices. So that's why I've been involved in the Coreboot community for most of the time. And Coreboot is an open source project that creates free firmware, sort of in the same way that Linux creates a free operating system kernel.
Before we're going to go into the technical details, we should probably set the scene, i.e., why is Coreboot so important and what happens if you turn on a computer. So let's start at the beginning. About 13.2 billion years ago, it all started. Also known as the Big Bang. Let's fast forward to the 60s. Martin, you were about 30 then, right? So you remember old iron as in the mainframes.
It depends which 60s, but yeah.
Anyway. The 1960s.
Ah, okay. Yes.
I'm talking about an architecture called /370, /360, that sort of thing. So you, as you may recall, you took a couple of punch cards and you fed this into a reader, and then you flicked the switch, and something called the IPL would take place, as in the initial program load, where actually set mainframe, as it was known then and now, and I reckon still now, would read these punch cards and did a couple of magic tricks. He initialized the hardware, feeding some of what is known as blobs into channel processors and all other magic stuff, and then finally, after a couple of days, would start operating on further punch cards he would feed into that machine, like COBOL, like Fortran, what have you. Again, let's fast forward another 15, make that 20 years. IBM has just introduced something called the PC, also known as the personal computer, and that personal computer came with something called a BIOS, as in a basic input-output system, not to be confused with any, what's the word I'm looking for, prejudices or something. So the main function of said BIOS would be, same thing, after powering up the computer, would jump to a predefined address and then would execute magic, like initializing the hardware, but also taking a look if we have a hard disk installed. Or if that's not the case, if we could initialize the floppy disk controller and see if actually a floppy disk is inserted into said drive. For the majority of the listeners, links maybe in the show notes, a floppy disk is an ancient storage device, about 600 years old. It did go...
Well, no, wait. It was actually quite modern. It succeeded the tapes, right?
Yes, I was just getting there, Martin.
Okay.
It underwent a revival in the late 70s. But the storage capacity was still quite limited. Having said that, one of the main functions of the BIOS was actually to load something from a device, from a storage device, and then if the signature of the so loaded chunk of memory would check out, it would then jump to this and then execute the code. So back in the 70s, this is how these PCs and PC XDs and all the rest of them worked. Fast forward again. It's now the 90s, maybe zeros. And this is basically, I hope, where Julius can take over. We have left the BIOS area and arrived at something called UEFI.
Yeah, so I can't really give you more context on that old mainframe stuff. That's before my generation. But
absolutely,
pick up with the PC BIOSes and go from there. I think one important point that maybe should be mentioned is that what you talked about is loading the operating system, which is an important part of what firmware does. But another important part that comes before that, that's usually the bigger part, is silicon initialization. That includes training the memory chips and doing a lot of other setup stuff that is needed to actually even get to the point where you can access a disk and actually load something from there. The IBM PC used this old BIOS, which wasn't really well specified. Kind of at the start, every PC did their own thing, and then kind of a standard slowly emerged, but it was based on the old x86 real mode, which was very hard to program, and so people didn't like it. And so I think it was mid-2000s roughly, Microsoft and a bunch of other companies started this UEFI effort, which is basically about redesigning everything that runs before the operating system from scratch and building a big concept about how all that should work. And they designed a system that is very complex, very flexible, very geared towards the normal standard desktop PC that we had back then, and less towards a lot of the other devices that we have nowadays, like phones and those kinds of things. Built on a bunch of technologies that Microsoft had already lying around and just threw in there. And so in the mind of us open source firmware developers, it kind of creates a lot of bloat and requires a lot of requirements to be added to the system that sort of slow the boot process down and make everything more complicated than it needs to be. So a bunch of people around that time started trying to develop an alternative to this. I think the actual Coreboot effort might have even started before the UEFI times. Originally, it was called Linux BIOS, and then was later renamed to Coreboot in 2008. And the main goal of the project is to create something that tries to be entirely open source and replaces this entire UEFI framework without actually implementing the UEFI specification. So UEFI is technically a spec that different vendors can implement, even though most vendors today build on the same source. It's a project called EDK2. But for Coreboot, due to the this bloat and all these extra requirements that get added by the specification, they basically try to go a different way and create something that can also boot the PC without going through all these extra steps, without adding all this extra stuff, and just trying to get the cleanest minimal solution that's necessary to make an operating system run, basically. And due to that, we have usually managed to, for example, achieve much better boot times than most UEFI systems, especially had back then and even still have nowadays. Like if you remember back in the 2000s, if you turned on your computer, you could basically go make a cup of coffee and come back in a minute.
Absolutely.
And then eventually it would be there. I think Coreboot back then really championed this booting under 10 seconds thing, and maybe some of that helped shame the industry into catching up a little bit, but I think they're still quite a bit behind what most Coreboot systems can do nowadays.
So what did you do faster than UEFI did?
Really, mostly we just do less. So UEFI just does a lot of stuff. It sets up a lot of services that the operating system can use if it wants to. And it one of the things about UEFI is that it's designed to have a lot of cooks in the kitchen, basically. So if you have a PC, then the CPU vendor makes your CPU, and other vendors may make certain extension cards that you put into the PC. And one of the core ideas of this UEFI-style BIOS is that each of these vendors can write their own code that initializes those specific devices. And they all want it to be closed source, of course, because they think it's like some super special IP they need to protect. And if it needs to be secure boot, then someone needs to sign all those closed sources, and each of them needs to have a different key, and someone needs to be at the top to have a manifest that signs all those separate keys. And it becomes this huge complex system of making all these different parts play together. And of course, release schedules also play into that. So you want one of those parties to be able to release an update to their part without all the other parties necessarily releasing updates at the same time. And so you need a pretty complex system to just glue all of that stuff together. Whereas in Coreboot, we just build from a single repository. All the code is in the same place. And it just makes it much easier to make things like the different components interact in a linear way that doesn't require all these extra interfaces and abstractions.
Resting on the security aspect for just a few more minutes, that really threw a spanner into the works, because I can recall certain comments from Canonical, i.e. the makers of Ubuntu, that they had to introduce a shim that would come with predefined keys that would allow Ubuntu to boot in a UEFI context, because otherwise UEFI wouldn't accept Ubuntu from a security perspective.
Right. So with UEFI, I think they tried to design secure boot into the system, but of course they didn't care about open source systems like Linux. So they basically just did whatever they needed for the commercial operating systems that the companies who were in this consortium cared about. And so I think Linux kind of came into this after the fact, and I'm not super familiar in the history, to be honest, but basically they already had the specification written, already had this system built where the operating system vendors needed to be able to sign something with those firmware vendors. And Linux kind of had to beg us after the fact for an option to get something signed that runs on these systems, but then boots whatever Linux kernel you currently want to boot that you probably built yourself, so you couldn't have Microsoft sign it or something like that. And that's how they came up with this shim method, which of course then takes out the security aspect, but still allows you to boot what you want to boot. Whereas with a system like Coreboot, in theory, you can build the entire boot security chain from firmware through your operating system yourself, sign your own kernel, and then basically get the same security without being tied to any of these companies.
We kind of missed a bit there. Why did Coreboot, or how did Coreboot come into existence? Since obviously UEFI was around before then.
Right. So Coreboot originally, like I said, it was originally called Linux BIOS. I think it was originally developed for not necessarily PCs, but high-performance computers, because there they also just had the desire to have something that boots faster and simpler than this. And so they originally the idea about Linux BIOS was actually to do very little in this firmware part itself and try to boot a Linux kernel from the same boot medium that the firmware is stored on, and then have that Linux kernel load an actual operating system from a disk or somewhere. We've kind of moved away from that idea, and around the mid-2000s, Coreboot became more of a traditional firmware that boots all the way to a kernel that's loaded from disk. But we still try to keep that idea of just not using this UEFI spec and bypassing all these complicated steps, and trying to design something that is both open source as far as we can do, and also tries to boot the operating system as fast as possible, with as little in between as necessary.
It's an interesting observation, because UEFI, if I recall correctly, was mostly aimed at Intel/AMD architectures, as in the traditional CPU architectures where the PCs originally came from back in the 70s, 80s. Now, fast forward once again, you have a slough of embedded systems these days. The device tree systems, and links, of course, will be in the show notes, in the kernel is just one example for the complexity of the hardware that you have to deal with. Then you have smartphones that come with 1 million or even more different SoCs, as a system on a chip, that have their own idea about the hardware requirements and all the rest of it. And then you have these devices in between, and Chromebooks probably are the best example, that are sitting somewhere in between an embedded device and a full-blown PC. So I reckon maybe now is the time to go into some high-level architecture aspects, because we don't want to get too technical, because, as I said, there will be links in the show notes. But how, for example, does Coreboot address this significant hardware complexity when it comes down to being a one-size-fits-all?
Yeah, I would say one size fits most. So there are definitely embedded devices for which Coreboot is not appropriate. Let's say your smart fridge or your smart lamp or something like that. Those kinds of tiny devices that usually run bare metal or with a simple RTOS on a microcontroller, that's not really the area that Coreboot targets. But everything that from a mobile phone up, basically everything that actually has a disk and loads an operating system from there, those kinds of more traditional devices, I think Coreboot can cover the whole range of that. You're right that the UEFI system was originally designed for the PC market and servers as well. And some of the remnants that were written in the specification with that in mind still kind of plague it today if you try to use it on smaller devices, even though people have tried. But I think today most smartphones still don't use UEFI. So Android, for example, uses its own thing. I'm not super familiar with iOS, but I think they also don't use UEFI. In Coreboot, how do we manage this? So first of all, one of the big differences is in architecture, right? So PCs traditionally use x86 chips most of the time, and phones tend to mostly use ARM chips. So Coreboot is designed as a fully architecture independent or like multi-architecture system. So just like in the Linux kernel, we have an architecture directory where we keep all the code that's specific to that, and we try to factor it out in a way that we can reuse as many components as possible and only need to separately implement the stuff that's really different between those architectures. Other than that, honestly, a modern mobile phone isn't that different in capability from a small laptop anymore. There's actually plenty of phones nowadays that are more powerful essentially than a laptop, like than a small netbook. And they tend to mostly boot the same way. They tend to have somewhat different components. Like your laptop will usually have an NVMe disk, whereas the phone usually has an eMMC or UFS disk. But other than those small changes in what kind of driver you need to write, the boot process tends to be pretty similar. And then the bigger difference is mostly about what kind of operating system you want to boot. Because if you want to boot Android, you need to do different things than if you want to boot Windows, for example.
Now it's probably the good time to walk us through, again on very high level, of what happens once you flick on the switch and then Coreboot takes over until you have a kernel in memory that is able to execute some sort of userland. System D comes to mind in traditional Linux systems. Other init systems are available, of course.
Right. So this, again, depends on the platform and the architecture. So for an x86 system, like this is basically standardized, and all the Intel and AMD chips all do the same thing. They start executing from first of all, we should maybe say the firmware is not stored on a disk. It is stored on a separate chip that's on the main board. It's called a spine or flash chip, and it's kind of connected to the CPU through a simpler interface than disks are. And when an x86 CPU boots, it just can directly start executing instructions from a specific offset on this chip. And there's a hardware controller built into the main board that can basically fetch this code from the chip and execute it in place at the time it runs. So it basically starts automatically fetching instructions from there and executing them. On the x86 systems, then the next thing we do is we do a bunch of processor initialization, like x86 processors start in this old real mode, like the old 80s PCs for downwards compatibility. So we have to switch up to the 64-bit mode that we use nowadays. Then the most important thing we need to do in initialization is turn on the memory and train it, because since the memory is not part of the CPU chip, but is usually a separate chip on the board, the connection between the CPU chip and the memory chips does not work by default. You have to actually initialize it and sort of do some training on there. And this is a pretty complicated process. And so we need to execute a bunch of code to do a bunch of back and forth testing on this connection, basically, until we figure out how to use it right.
Sorry, I was just going to ask, what do you mean by the training of the memory?
So basically imagine that if you have two chips on a main board, right, and they may not be right next to each other, so you need to connect them through lines on the board. And possibly those lines might go at a right angle, right, depending on how you place the chips. And if you have a parallel bus with 64 lines that have a right angle, then the lines on the outside of this bus are going to be slightly longer than the lines on the inside. And that means that if you try to use this as a parallel bus and send bits over those lines, the bits on the inside are going to reach that chip faster than the bits on the outside. And if you just naively try to use this as a parallel bus, you will not be able to achieve high speeds, because at some point that difference in timing is going to be enough to make the connection not work anymore. So you basically, before you use it, you have to test each of those lines and sort of measure the delay between when does the bit on the innermost line arrive versus the outermost, and program specific delays for each of these specific pins, so that you know when to measure the bit that returns from the chip, basically. And that's a pretty complicated process. And it's actually also one of the parts that the vendors of these CPU chips and memory chips try to keep confidential nowadays, because they have special tricks there that make it more efficient. And so even though Coreboot is an open source firmware system, unfortunately, we do need to run some proprietary blobs inside of the boot process that that basically there's no open source solution for. And memory training usually tends to be one of those things that require a blob on almost every platform that cannot be open sourced. So that's one of the things that you do. You do a bunch of other silicon initialization, which also may involve other blobs. Like there's a lot of clocks and power regulators just inside a chip that turn on different components of that chip that usually all need to be turned on during this initial boot process, so that you can do things like talk to your disk controller and actually talk to the disk through that. And then after all that silicon initialization, you eventually get to the actual bootloading part. That is actually not part of Coreboot, but instead Coreboot has the system called a payload, where it loads a separate binary that is specifically written for bootloading. And
Julius, before we go there, let's spend some more cycles on this memory training, because we're talking about memory on the same board, because there's also a concept that was all the rage about 20, 30 years ago called NUMA, as in where you could basically page in a couple of virtual memory pages from the other side of the planet if the hardware would play along. But this has nothing to do with that, right? It's just local RAM capacity on the local board.
Yeah, so this is only about the basically, if you open your PC, you probably know there's like a bunch of slots where you can put in the memory chips, like the DIMM boards. And this is talking about training those. So because those have these connections that I mentioned that need to be measured first before they can be used, you cannot talk to them directly when the system starts. And that's actually one of the things that makes firmware development so tricky, because in that early part, before you have this memory training done, you do not have memory. So you don't actually... it's a very complicated programming environment, because you still need to, of course, store the data that your program uses somewhere. And different platforms have different tricks to get around this problem. For the x86 boards, the usual concept is called cache as RAM. So you know that the CPU itself has a bit of memory built into the chip. That's the cache, which is used to usually give you faster access to memory data that you've used recently. When the system boots, you can put the chip in a special mode where it treats this cache differently and basically pretends that it can be directly addressed by the program. And then you can use it as a sort of makeshift memory for that early part where you're running the memory training code until you can access your actual memory. On other platforms, like some of the ARM chips that are usually used in phones, they have a separate bit of memory that's called SRAM on the chip that is kind of similar to caching technology. It's just not used that way. So they basically just have put aside a couple 100 kilobytes just for handling this boot process and any other processes where memory may for a certain time not become not available.
As far as I know, basically, also memory chips age over time, so the timing specs may differ, may not differ, but rather, what's what I'm looking for? Slide over time, right? So, like, if you let's stick to the simple example of a server. If your server is a couple of years old, has been running 24/7, only basically being powered down for maintenance cycles, the timing behavior of said RAM chips on the board may be different, right? If I recall
Right.
correctly.
So, yeah, and that's basically the reason why we do it on every boot, right? Because otherwise you could say, why don't you do this once, like in the factory when the computer is produced, and then just store the timing values there? But like you said, they do shift over time and with different temperatures, so it's important to keep redoing it regularly. And usually systems tend to have a mix between those two modes where we do have the code to fully retrain the memory and firmware, but we also store the last training data from the last boot. And then on the next boot, we just kind of reuse that data and compare and try to check, is it still valid? And if it is, then we can finish the training process very quickly. We just basically double check that the last data is still applicable. And if it isn't, then we need to do the full retraining. And the retraining can actually take quite a bit of time. So on these, this has become much worse with recent memory technologies. So back with DDR3 and 10 years ago, it was still usually done in a second or less. So you didn't really notice it during the boot process. But with these modern DDR4, DDR5 technologies, it can sometimes take half a minute or so. And that's really noticeable. So because of that reason, we have we come to the point where we need to do more innovating in the firmware space to at least give the user some notice that this is happening, because otherwise you turn your computer on and it just doesn't do anything for half a minute and you got confused and you maybe start hard resetting it, which of course interrupts this process. So we need to figure out ways to teach the users not to do that. And that's become a more recent, an interesting problem more recently.
I mean, you can't do much without the memory being initialized, so you can't even print something on the screen saying, sorry, we're training memory, please wait.
On some systems, we can actually. So especially some of these x86 systems, they do have display controllers which can be put in certain modes that you can at least display text messages before the memory is up. On some other systems, we don't have a way to do that, and then we just need to try to optimize this training process as far as possible and then live with the remaining time that we have.
Okay, now the CPU has been initialized, the memory has been trained, but there are still the trillions of SoC components, either as part of the almost synthesized CPU die, but also in smartphones being on separate devices. In the traditional Intel systems or PC systems, they would be known as South and North Bridge, right? So what happens afterwards in terms of how do you cope with the complexity? Of course, device trees come to mind in embedded systems, but I reckon there's many more concepts than just device trees for going about how to deal with the complexity of the hardware initialization before you even load the kernel.
Yeah, so the concepts of South Bridge and North Bridge pretty much died, I think, 15 years ago or so. Nowadays, I'm not super familiar with the Intel platforms, but I think they basically have everything on one chip. There used to be a thing called the Platform Controller Hub, which was basically the combined, I think, just the South Bridge, because the North Bridge moved into the CPU even earlier than that. Nowadays, I think, if I'm correct, even that has moved into the CPU chip. So it's basically all one system on chip, even on the Intel side, even if they don't necessarily use the terminology. And on the ARM side, these system on chips have been more common even in the past. But you're right,
Julius, I'm old. Yeah, and it does show, sorry.
But you're right that they do have a lot of components that need special initialization. And but the fact that it's all on the same chip makes it easier, because then you only need to target that one chip, right? You don't have this complexity matrix of different components that could be plugged together. So that, I think, actually made things a bit simpler for us. And then the remaining things we have to initialize is everything that's outside of that chip, which is mostly the disk, sometimes the network if you want to boot from network, and of course the memory. But most of those interfaces are honestly pretty standardized. So you have your NVMe driver, and then the NVMe system is designed so it can build to any kind of NVMe disk that's attached to the other side. So on that end, I think the complexity is pretty manageable. Inside the SoC, we also have something in Coreboot that's like device trees, like you mentioned. So Coreboot has its own format of device tree that it just uses to describe everything that's inside the chip and some of the other parts that are connected to the outside, like some smaller battery charging control things and so on that are connected to smaller buses. And we do have a sort of a description language that we can use to easily describe all of those. And then that gets compiled into C code in the backend, and we can use access that as part of the normal code inside of our firmware program. I don't know if that makes sense.
Oh, it does. Changing tack just a little bit. Now that we have covered the hardware, if I take a look at the GitHub repo, I notice that you're using a very ancient programming language called C. I reckon because of the history of Coreboot, it was the technology of choice at the time, but I won't go as far as discussing Haskell or Ada in the context, but need to say with the advent of Rust and some other system-oriented languages, are there any plans to re-implement portions of Coreboot in that technology? Or why didn't you consider C++ instead of C? If you can speak to this.
Right. So there is actually a bit of Ada code in Coreboot that's used on some platforms.
There is, okay.
Yeah. That was put there, though, by one enthusiast in our community, and nobody else knows how to touch it, so that's a bit of a problem. And that is basically also the main reason why we use C, right? You're right that nowadays better languages exist, and even back then, technically, better languages existed, but a lot of the things that drive these decisions are just what do people know. And since in this space, the Coreboot community cannot implement support for all new platforms on their own, right? Usually the vendor of a chip implements the Coreboot support for that chip. And those vendors all have engineers that know C and not whatever weird language we would like to use, right? So we kind of have to meet them where they are. And the entire systems engineering community, I would say, that's also why Linux is in C, right? Because all these companies that have engineers who work on this boundary between hardware and software, everyone knows C, but few people know other things. Even C++, I think, in the hardware driver space is not that well known. So C tends to be kind of the common lingo there where we all meet, and that's why it's still the most practical thing to do these. There has been actually a project to completely rewrite Coreboot in Rust, which is called Coreboot, because it's Coreboot without C, right? So, but they sort of had a prototype, and I think they've got it to work on some systems, but it's not really something that's taking off, mostly because of this reason, because you can't get companies that you want to support their new chips on to implement stuff in Rust for you, because they just don't have the engineers and the know-how to do that. In the same way, in our community, there's not that many people who actually are familiar with Rust. So we have been thinking about doing the same thing that Linux is doing now, which is just taking small components out of the C code and re-implementing those in Rust, and then having an interface between those components and the bigger part that's still in C. And I think that's the only reasonable way how you can slowly move towards a more Rust-based firmware ecosystem. But for now, that's just an idea, and Coreboot is still fully in C.
I mean, Linus was pretty clear about C++ and why he wouldn't approve any pull requests. And you're talking about early 90s now, maybe mid 90s. Links will, of course, be in the show notes. Why C wasn't a runoff for the kernel as such. But Linus is pretty, I'm tempted to say, leaning towards Rust, because that goes back to a Plumbers conference, I think, in 2018, 2017, where some people started to implement a couple of crates for interfacing secure or safe Rust code with unsafe C code, mostly for device drivers now. But that work has come a long way, and I reckon more and more Rust will enter the Linux kernel. So it's interesting to see that a similar effort takes place actually in Coreboot.
Yeah, I mean, we are definitely not as far ahead in this space as Linux is. So I think part of that is also that Rust has only been used as like a kernel and firmware kind of engineering language pretty recently, and there's still some some small issues to work out there. So we've basically let Linux and certain other more embedded projects lead the way on that, and once those techniques are better developed, and once Rust has also actually been fixed to get around some of the code size issues and so on that they had a couple of years ago still in that space, I think then it will be easier for us to also move into that space. So I think we're basically sitting back right now and seeing how this effort goes for Linux and how it turns out for them. And if they have success with that, we would probably want to copy it, because clearly Rust does have a big advantage, right? I think it's undeniable that there's a good reason to go to Rust. It's just the question is it practical, and can you actually how can you actually do it?
Well, yes, I mean, there's definitely advantages to Rust, but not everybody is convinced, as we know. Anyway.
Martin would be the prime example for this, but we're going to go about this in the next few years.
This is the same as Julius's point, right? It's the majority of the people maintaining these things are C programmers. So, yeah, it's not going to happen anytime soon, just changing it all. I mean, to be fair, lots of developers like to, what they call refactor stuff, just rewrite it all. I was going to ask, so you mentioned companies contributing to Coreboot. What does the Coreboot community look like in terms of who's supporting it and who are actually the people that are building this project? Apart from yourself, of course.
Yeah, I think it's kind of a good mix between company engineers and people who are just enthusiasts and have been there for a long time because they just like working on firmware. So, of course, a lot of our code contributions come from companies because they just, have the time because we get paid to do this on the job. But there's a lot of people in the Coreboot community who are just there for the fun of it, who've been there for a long time, who just like to figure out how this works or like hack around on their own mainboard, those kinds of things. And they help keep the Coreboot community a real open source community, because some of those other open source projects that are only founded by companies tend to be only open source in name, but not really in spirit. Yeah. I think Coreboot is a very different project because we really do have a lot of those people who care about open sourcing all the stuff that they need to run on their mainboard, basically, who care about the open source idea, who keep pushing back on all those vendors who want us to move more of the stuff that we're actually doing into these blobs that I mentioned. And we kind of tend to have a constant fight with companies like Intel and other chip vendors who would really prefer that everything is in a blob and Coreboot is just an empty shell around it. And we want it to be the other way, that Coreboot actually does most of the things and the parts that aren't open source are as small as possible.
So the Intels of the world, they don't contribute to Coreboot. I guess they just want to keep it all.
No. Intel definitely contributes to Coreboot. Okay. Like they're a big contributor, but they also have different ideas of how they want Coreboot to look like, right? And the people who care about the open source spirit most, I think, have a different idea from Intel and how they would want those things to work. Of course, Intel has other incentives, like this blob that I mentioned, they call the firmware support package, is not just used by Coreboot, it is also used by other firmware projects. So, of course, for Intel, it makes sense to have everything in there because then they only need to have it once. But for Coreboot, we want everything, or as much as possible, to be outside of there so that we have the control of changing it to whatever we want, taking parts out that we think we don't need, those kinds of things. So it's always a back and forth in deciding these things whenever someone wants something to change, right? Whenever they have a new thing on a new chip that needs to be done, we need to have this discussion of how much of it is going to be initialized in Coreboot versus inside the FSP. But Intel definitely does contribute to Coreboot, and we wouldn't be able to support all their recent chips without their help. So they're doing a lot. I'm not trying to say they aren't.
Excellent. So is there some kind of steering committee or something like that in the Coreboot project, or how does it go up the chain in terms of what decisions are made and things like that?
The dreaded governance question. Yes, Martin, indeed.
Well, they all do it differently, right? So that's why I'm curious. Yeah.
Yes.
Yeah, I think a pretty lightweight solution for that. There's a committee of 3 people that are officially the Coreboot leadership, but they tend to have a pretty low-touch approach on this. And for most of the things that are decided in the community, we have a meeting every 2 weeks that most of the people who are interested show up to. And whenever there's an issue, we just try to talk it out, find a compromise, those kinds of things. When we really do have a problem, then that leadership committee decides, and they take into account mostly the opinions of the people who've been there for a long time and contributed much to the project. But for the most part, it's a pretty unofficial process, and we try to work by consensus and we try to talk things out. And we do have a mailing list too, where we can have lively discussions, because there are many different opinions, especially about this blob issue, right? And about how much are we going to allow companies to keep things closed source, and at what point do we say that we can't use this in Coreboot anymore? And we always, have a lot of discussions there, but we don't have a big, we don't have a single leader, and we don't tend to have big top-down discussions.
Okay. So let's talk about. You work for Google and Chromebooks and stuff like that. Presumably, it's used there. But is there any other as a commercial adoption of Coreboot there that you can talk about?
In the personal computing market, I'm not so sure. There used to be a company called Purism, I think, that made laptops that came pre-flashed with Coreboot. I don't know if they still exist, to be honest.
They're also known for phones, I might add.
Okay, then you know more than me in that area. So.
Yeah. I mean, they had it was called LibrePhone or something like that. It was one of the first pure FLOSS plays in the mobile phone space. Links maybe in the show notes if I can't remember. But go ahead, Julius.
Yeah, so that's the one case I know. I think there might be some others, but they're pretty minor, so you kind of have to look for them. There's no big PC vendor other than Chrome OS, which actually uses Coreboot as their main system. So if you want a system that runs Coreboot, really buying a Chromebook is one of the easiest ways to achieve that, because they all do that. And they're all designed so that you can actually reflash the Coreboot on it and replace it with your own the stuff you built yourself and so on, if you unlock it sufficiently. They're also used in the server markets in some cases. I don't want to name specific companies because I'm not super sure about the details, but I think some companies do use Coreboot in their internal servers because they also want to have more control and don't want to leave everything up to the people who implement this UEFI bias. So we tend to see a bunch of companies moving towards Coreboot because it gives them that freedom to decide their own fate in the firmware space, basically.
I mean, it does make sense because more and more, and the hyperscalers are an excellent example for this, more and more companies are moving away from Intel architectures or AMD architectures towards ARM-based boards, also or predominantly in the server space. HP entered this about 15 years ago with a project called Moonlight or Moonshine or something. Eventually, they decided to do phase 0 of the project with sub-spec Intels, but ARM was clearly on a couple of boards I saw when I was working in that space. And I reckon things have progressed since then. You'll see this actually if you go into any hyperscaler of choice. You actually see if you deploy a VM, you have the choice between ARM and Intel-based hardware or AMD-based hardware.
Yeah, that's true. I will add that not all ARM, there's also ARM systems which do use UEFI, right? Especially in the server space. There are some reasons why certain companies prefer the UEFI solution and is alive and well in that space. But we do also have, especially in the mobile phone space, like I said, there are different solutions that are usually not UEFI based, but not all of them use Coreboot either. There are other mobile phone bootloaders that are often used in that space. I think it's more of a contest between the company that makes the CPU chip, which usually has their own solution, which is often not Coreboot based, and the platform integrator who may have an interest in doing their own firmware and not leaving everything up to the chip maker.
Okay. Taking a look at the GitHub, we're changing tack just a little bit for the time being. I noticed that Coreboot itself is licensed under GPL version 2. It's interesting because how does this cope? I'm almost tempted to say with the non-open source nature of said blobs and other components that are not exactly open source to the community in terms of provided by the hardware vendors.
Right. So these blobs that I talked about, they all essentially work like different programs. They are not linked into Coreboot as a library into the same program. So we do not violate the GPL in that way. It's basically just like if you have a script that calls another binary to do something, it's kind of the same except implemented in firmware. But we do need to make sure that every time we integrate one of those things, we actually keep it very separate, like a separate program that is jumped to, and then that either jumps back to us at the end or to the next Coreboot stage. But we can't have the kind of tight integration that you would have with the library because of this reason, because we care about being GPL and being fully open source for the Coreboot parts.
So a more permissive license like BSD or the BSDs of the world or something like that, in order to even foster adoption beyond the copyleft aspect, wasn't a choice at the time.
The decision to use GPL is a lot older than I've been in the project, so I'm not sure what led to that. I think one of the reasons maybe
Julius, sorry, I'm not trying to shoot the messenger here, but I just noticed that. Sorry, so.
Yeah, I mean, one of the things I want to mention is we do like to import code from other GPL projects at sometimes. So I think that may be a big reason to do that, because the U-Boot project, which is a different bootloader that sometimes implements a certain platform before we do, is a GPL. So if we want to take a driver from that, we also have to be GPL. Linux, of course, is GPL. So oftentimes when we develop a driver for some new hardware that Linux already has, we look at that driver, we maybe take certain pieces, and we can only do that if we are GPL. And of course, being BSD is always dangerous for a project like this, because you cannot force anyone using you to contribute back. And in a space like Coreboot, it's of course easy to see that companies might just want to take Coreboot, implement their own chip and use it, and maybe wouldn't contribute back in that case. So I think we do gain from using the GPL because they can't do that basically, and that way we can actually keep the project alive by getting all of these contributions back.
Interesting. You just mentioned U-Boot there. Full disclosure, every now and then I'm just game for embedded systems hacking. So JTAG to debug some boards. It's a nature of choice. JTAG, for the youngsters listening, JTAG is an ancient technology that allows you to debug a board using a serial connection that is tied to a terminal, and then you can see actually what's happening once the main CPU boots up. Gummiboot or Gummiboot, whatever it's called in English, would be a spin of U-Boot, if I'm not completely mistaken. These are also present not just in embedded space. I'm just wondering, would you consider them to be competition because you mentioned them, or would you consider them to be kind of neighbors, friends, what have you?
I would say both. I mean, there are definitely platforms where there's both a U-Boot solution and a Coreboot solution, and whoever is like the platform integrator can choose which one works better for them. I think U-Boot has originally been more focused on this embedded ARM device kind of space, and possibly mobile phones too, I'm not sure. And Coreboot has originated from the PC space and then kind of moved into that. So we both came from different points, but kind of merged in the middle as we expanded. I think U-Boot does certain things a lot differently than Coreboot. I think Coreboot has there's good reasons to pick one or the other depending on what you want. Like U-Boot traditionally, for example, has this big built-in command line that a lot of people like because they can do a lot of debugging. So that might be a reason why you want to pick U-Boot. Coreboot intentionally never did something like that because we feel that it may harm the boot flow, or it makes optimizing boot time harder if you integrate UI features like that. Coreboot also, since it came from the x86 space but then expanded into the ARM space pretty early, I think we have very good multi-architecture support, and we are very good at sort of factoring out the differences between the architectures in a way that we can reuse a lot of our stuff across all of them. Whereas U-Boot, while it does support multiple architectures, I think the x86 support in U-Boot has always been kind of the neglected stepchild. So I think they are not as good in that space as Coreboot is. And Coreboot has a good solution for storing extra files inside the Flash image that certain platforms may need. Like we have this thing called the Coreboot file system, which is a pretty good, pretty extensive solution for storing all the extra stuff that maybe a certain platform needs. Whereas U-Boot, I think, as last I checked, which to be honest has been 10 years ago, didn't have a good solution for those kinds of problems. So depending on what you want, depending on what your goal is, and depending on whether your platform is supported in one or the other, there may be good reasons to pick U-Boot or Coreboot.
Interesting. Let's put it this way. Final question: where do you see this going, and what would you perceive as the main challenges or the main challenge going forward?
Our goal is, of course, to make open source firmware possible on as many devices as we can. So where we want to see this going.
So this is world domination as usual. Sorry for interrupting.
Of course, yeah. But the way we want to see this going is to get Coreboot adopted in more systems, to make sure we always have support for the latest new Intel chips or whatever that comes out, to basically support as many platforms as possible, and to encourage adoption also among OEMs who sell ready-made PCs. Like we would love to see more OEMs just selling you a PC with Coreboot already pre-installed, of course. The challenges that I see is honestly mostly this constant fight with the chip vendor, who often has an incentive to try to close more things down and therefore kind of always stands opposed to projects like Coreboot. So while we do have a good relationship with a lot of chip vendors and they do contribute, I think a lot of them also have incentives to keep pushing their own UEFI-based solutions and to come up with new things that are difficult for Coreboot to support, or that kind of take some agency from Coreboot away. And so our biggest challenge is always to make sure we keep staying in that game and we keep being able to support all those new platforms, and we don't just get left behind because of some industry change or something.
Makes sense. I was going to finally ask, you mentioned the blobs and stuff like that. How is that progressing in terms of making some of that code more open? Is that getting better, or will that remain the same? How do you see that over the last few years and into the future?
Especially before you answer that, we should probably also touch upon LibreBoot in this particular context, because LibreBoot, of course, would be, and correct me if I got this wrong, Coreboot without any closed source components.
Yeah, so LibreBoot, my understanding is that it's basically just like a packaging script for Coreboot. Like they take our code and they basically trim all the options until, like, the configuration options are only those remain that fit whatever description of free they use. So they don't add new code or new support for extra platforms that we don't have. So they just take what we have and cut it down to what they like. The problem is that recently we don't have many platforms that can be fully blob free anymore. Like that used to be kind of the case, 10 years ago. You could still find some mainboards where someone had reverse engineered the memory training, and you could use that without using the vendor blob. I don't think we have many platforms like that anymore. Unfortunately, since you asked in what direction it's moving, unfortunately, it's been kind of moving in the wrong direction from our perspective for a while. With these newer memory technologies like DDR4, DDR5, vendors have become much more concerned about open source memory training code. And I think for those technologies, I'm not actually aware that we have any implementation that's fully open source anymore. So I think back in the DDR3 days, back in 2015-ish, were about the last time we actually had platforms that could boot fully open source without any blobs all the way. And ever since, we've been, like I said, trying to fight this fight of remaining relevant, being able to support newer platforms, but having to kind of make unfortunate compromises just to be able to get anything that can still boot, basically. So I'm not trying to be a doomer here. I still think open source firmware has a great future ahead of itself, but there are certainly challenges, and it is a constant fight, and we do have to build good relationships with these chip vendors to also convince them of why it's important what we are doing and why we need them to support this use case as well, and kind of constantly try to fight this fight and make sure we manage a way forward, even though there are other concerns from their side.
Martin, any very final questions before we go to the boxes?
No, that's been very insightful for sure.
Okay. Over to the boxes. Martin, so what's your box?
Oh, my box is it's in fact 3. Two grumpies and one vampirus.
Go ahead.
No, it's our colleagues, the grumpy old coders, who are occasionally making a podcast episode. We had a great recording with them.
Fair enough.
And of course our regular vampirus who's turning up for Halloween.
Yes, our beloved countess. Yes. Vladessa, if you're listening, Martin is currently working on the next Halloween episode, so stay tuned.
It's going to be only a few days long, yeah.
Yes, and I'm dead sure that Hollywood will feature in this episode. By the sound of it. Yes. So, Julius, over to you. What's your pox?
My pox is just Chromebooks, basically. Kind of chilling.
Okay, fair enough.
So I would say if to anyone who has never tried one, I would encourage you to just check them out, especially for those kinds of cases where, for example, you're trying to get a laptop for your parents and you want it to be very easy to use and want it to be something that you cannot really mess up in a way that you have to come and fix it for them. It's a really good device for those kinds. No, I'm serious, though. Like, I've hooked up my whole family with them, and basically everyone who's tried them said they were very happy with it. And
is there some kind of try before you buy scheme for these Chromebooks or something? Or have I missed this?
Martin might be particularly interested in this.
I remember having to shell out some cash.
Within 30 days or something, but I don't know.
Google, if you're listening, the email address is sponsor@linux.eu.
Yes, and take over their marketing.
Just send about 20 samples to the address that you will get once you send a mail to this email address, so that Martin can max himself out.
Yeah,
you only need one, right?
Well, you have at least one, if not.
I have at least one, and it's how old is this? Hang on, let me think. This is probably around 10 years old. Yeah.
Is it? 10 years.
Yeah.
Okay.
It doesn't have much memory. It weighs nothing, but it does.
Well, I mean, it
various standard things.
I mean, it doesn't do much, right? Because it boots up, opens the browser, and then. Yeah. It connects to the cloud. Simple as that.
This is it. Everything runs in the cloud these days.
Indeed. Apart from the stuff that you don't want to hand over to the hyperscalers.
There's obviously a downside when the cloud doesn't work, but hey.
Yes, exactly, Martin. That's precisely my point. Anyway, going back to my Cheffer grounds, my POC is actually, and we featured this before, a podcast also known as the Software Freedom Podcast, done by our beloved friends, the Free Software Foundation Europe. We mentioned them before, but it's worth doing this just again because it's such a great podcast. And they did a little bit of tweaking. And if you are into the, I'm almost going to say, political side of free Libre open source software, this is a podcast you don't want to miss. And with that, we would like to thank Julius. Julius, thank you very much for being there. It has been more than insightful.
Yeah, thanks for having me. Definitely, it was fun.
Yeah, and Martin will get in touch about these 20 plus Chromebook samples.
Other numbers are an option too.
I do have a box on my desk, but I'm allowed to share it.
And with that, people, see you soon.
This is the Linux In-Laws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
We hope you like this feature presentation. If so, please spread the word. If not, please let us know. Feedback at linuxinlaws.eu.